Welcome! In this session, we'll tackle a fascinating problem often encountered in coding interviews, problem number 1344, angle between hands of a clock. We'll explore how to calculate the smaller angle between the hour and minute hands of a clock. It's a great mix of math and logical thinking, so let's dive in. In this problem, we're tasked with finding the smaller angle, in degrees, formed between the hour and minute hands of a clock. First, let's break this down. The hour hand completes a full 360-degree rotation in 12 hours, which means it moves 30 degrees per hour. Similarly, the minute hand completes a full rotation in just 60 minutes, so it moves 6 degrees per minute. Importantly, as the minutes progress, the hour hand doesn't stay fixed, it moves slightly as well. Specifically, it moves 0.5 degrees for each minute that passes. To solve the problem, we calculate the absolute difference between the angles formed by the two hands, and since the clock divides into two regions, we return the smaller of the two possible angles. The inputs to the problem are the hour and minute values, and the output is a floating point number representing this smaller angle. Let's explore some examples to understand this better. In the first example, the input is hour equals 12 and minutes equals 30. Here's how we calculate the angles. The minute hand is at 30 minutes, so its angle from the 12 o'clock position is 30 multiplied by 6, which equals 180 degrees. The hour hand starts at 12, but it moves slightly as 30 minutes pass. Its angle is calculated as 12 multiplied by 30 for the full hour, plus 30 multiplied by 0.5 for the minutes passed. This gives us 0 plus 15, so the hour hand is at 15 degrees. The absolute difference between the two angles is the larger angle, 180, minus the smaller angle, 15, which equals 165 degrees. Since this is already the smaller of the two possible angles, we return 165.0 as the result. Now, consider the second example where the input is hour equals 3 and minutes equals 15. Here, the minute hand is at 15 minutes, so its angle is 15 multiplied by 6, which equals 90 degrees. For the hour hand, it starts at 3, meaning its base angle is 3 multiplied by 30, which is 90 degrees, but it also moves slightly as 15 minutes pass. This additional movement is 15 multiplied by 0.5, which equals 7.5 degrees. Adding these together, the hour hand is at 97.5 degrees. The absolute difference between the two angles is 97.5 minus 90, which equals 7.5 degrees. Since this is the smaller of the two possible angles, we return 7.5 as the result. Let's look at one more example. In the third example, the input is hour equals 6 and minutes equals 0. The minute hand is at 0 minutes, so its angle remains at 0 degrees. The hour hand is positioned at 6, so its angle is calculated as 6 multiplied by 30, which equals 180 degrees. The absolute difference between the two angles is 180 minus 0, which equals 180 degrees. Since the smaller angle between the two hands is always returned, we output 180.0. To summarize, the problem has constraints ensuring valid hour and minute inputs, and the result is always a floating point number rounded to one decimal place if necessary. Edge cases include scenarios like both hands overlapping at 12 o'clock, resulting in an angle of 0 degrees, or hands being opposite at 6 o'clock, resulting in an angle of 180 degrees. These considerations help ensure the solution handles all possible inputs correctly. To solve the problem of finding the smallest angle between the hour and minute hands of a clock, we can consider several approaches. The first is a brute force approach, where we simulate the positions of the hour and minute hands by iterating through all possible times on the clock. For each time, we calculate the angles of the hands and determine the absolute difference. However, this approach is computationally expensive because it involves unnecessary iterations and redundant calculations, making it inefficient. A better alternative is the mathematical calculation approach, where we directly compute the positions of the hour and minute hands using formulas. For instance, we know the hour hand moves 30 degrees per hour and an additional 0.5 degrees for every minute. Similarly, the minute hand moves 6 degrees per minute. By leveraging these observations, we can calculate the absolute difference between the two angles and return the smaller of this difference and its complement, which is 360 degrees minus the absolute difference. This approach is not only more efficient but also avoids redundant computations entirely. Using the mathematical calculation approach, we can break down the solution into a clear sequence of steps. First, we calculate the angle of the hour hand using the formula hour_angle equals hour percent 12 asterisk 30 plus minutes asterisk 0.5. This accounts for the hour hand's movement based on both the hour and the minute input. Next, we compute the angle of the minute hand with the formula minute_angle equals minutes asterisk 6. With these two angles, we can find their absolute difference using angle_difference equals abs, hour_angle, minute_angle. Finally, we return the smaller of this difference and its complement, calculated as 360 angle_difference. This ensures that we always return the lesser of the two potential angles. The time and space complexity of this approach are both constant, 1, as the calculations involve only direct, fixed computations without any loops or additional memory usage. While there are alternative approaches, such as simulating the clock's behavior dynamically, these are less efficient and unnecessary given the elegance and simplicity of this mathematical method. When comparing these approaches, the trade-offs become clear. The brute force approach, while straightforward to conceptualize, is highly inefficient due to its iterative nature and high computational cost, making it impractical for real-time calculations. Clock simulation, though intriguing, adds unnecessary complexity to what is fundamentally a mathematical problem, making it less appealing. In contrast, the optimized mathematical approach stands out for its clarity and efficiency. By focusing on the angular relationships and movement of clock hands, this method provides a concise and elegant solution that operates in constant time. This efficiency, combined with its straightforward implementation, makes it the ideal choice for solving this problem. Overall, this strategy balances simplicity, performance, and accuracy, ensuring a robust and effective solution to the given problem. The goal of this problem is to calculate the smaller angle formed between the hour and minute hands of a clock. For instance, if the input is hour equals 3 and minutes equals 15, the smaller angle would be 7.5 degrees. To break this down, the algorithm starts by normalizing the hour input since clock hours are cyclical from 1 to 12. If the hour value exceeds 12, we reduce it using the modulo operation, hour percent 12. This step ensures the algorithm handles any input, even unexpected ones like hour equals 15, which simplifies to 15% 12 equals 3. Once the hour is normalized, we calculate the angle of the hour hand. The hour hand moves 30 degrees per hour, and for every minute that passes, it moves an additional 0.5 degrees. This is represented by the formula, hour asterisk 30, plus, minutes asterisk 0.5. This allows us to precisely locate the hour hand's position on the clock face, considering both the hour and the minute inputs. To see this formula in action, let's calculate the hour hand's position for hour equals 3 and minutes equals 15. Substituting the values, we get hour_angle equals open parenthesis 3 times 30 close parenthesis plus open parenthesis 15 times 0.5 close parenthesis is equal to 90 plus 7.5 is equal to 97.5 degrees. This means the hour hand is at 97.5 degrees from the 12 o'clock position. Next, we calculate the position of the minute hand. The minute hand moves 6 degrees for each minute, which is derived from dividing the full 360 degrees of the clock face by 60 minutes. The formula is minute_angle equals minutes asterisk 6. For minutes equals 15, the calculation becomes minute_angle is equal to 15 times 6 equals 90 degrees. With the positions of both the hour and minute hands determined, the next step is to calculate the absolute difference between these two angles. This is done using the formula absolute_difference equals abs, hour_angle, minute_angle, ensuring the result is always positive. Using the values we've calculated so far, where hour_angle equals 97.5 and minute_angle equals 90, we find the absolute difference by substituting into the formula, absolute_difference equals abs, 97.5 to 90, equals 7.5 degrees. This gives us the difference between the two hand positions, but remember, the clock is circular. The absolute difference could represent the larger angle formed between the hands if it exceeds 180 degrees. To ensure we always get the smaller angle, we compare the absolute difference to its complement on the clock, calculated as 360 absolute_difference. The smaller of these two values is what we return as the final result. For our example, with absolute underscore difference equals 7.5, the smaller angle is min 7.5, 360 to 7.5 equals 7.5 degrees. This confirms that the smaller angle formed between the hour and minute hands is indeed 7.5 degrees. Let's take a moment to highlight some key aspects of this algorithm. First, the hour hand moves incrementally based on both the hour and the minutes, which is why we include the minutes asterisk 0.5 term in its calculation. This ensures that the hour hand's position is calculated with precision. Second, normalizing the hour input using hour %12 is critical for handling edge cases, such as when the hour input exceeds 12. Third, calculating the smaller angle by considering the minimum of the absolute difference and its complement to 360 degrees accounts for the circular nature of the clock. As for data structures, this algorithm doesn't require anything complex. It relies purely on arithmetic operations and a few variables to store intermediate results, such as hour underscore angle, minute underscore angle, absolute underscore difference, and smaller underscore angle. This simplicity ensures that the solution remains efficient and easy to implement. Finally, let's address edge cases and the performance of this algorithm. For instances like midnight or noon, where hour equals 12 and minutes equals 0, both hands overlap, resulting in an angle of 0 degrees. Similarly, for exact hour marks like hour equals x and minutes equals 0, the angle is always a multiple of 30 degrees. If the input contains invalid values, such as minutes 60, the algorithm should either normalize or reject these inputs, depending on the problem's constraints. Regarding complexity, the algorithm is highly efficient. Its time complexity is O(1), because it performs a constant number of arithmetic operations regardless of the inputs. The space complexity is also O(1), since no additional data structures are used. This makes the solution both robust and optimal for the problem at hand. This Python implementation solves LeetCode problem number 1344, angle between hands of a clock. The goal is to compute the smaller angle between the hour and minute hands of a standard analog clock. The function angleClock takes two parameters, hour and minutes, representing the current hour and minute on the clock. Here's the step-by-step explanation. 1. Hour hand calculation. The hour hand moves 30 degrees per hour, 360 degrees divided by 12 hours. Additionally, the hour hand moves slightly with the minutes. This is calculated as minutes/60 *30. The formula, hour %12 *30 plus minutes/60 *30 gives the total angle of the hour hand from the 12 o'clock position. 2. Minute hand calculation. The minute hand moves 6 degrees per minute, 360 degrees divided by 60 minutes. Thus, the angle of the minute hand from the 12 o'clock position is minutes *6. 3. Angle calculation. The absolute difference between the hour hand angle and the minute hand angle is computed using ABS, hour underscore angle, minute underscore angle. This gives one of the two possible angles formed between the hands. For smaller angle, since a clock is circular, the smaller angle is the minimum of the computed angle and its complement, 360 degrees minus the angle. This is achieved using min, angle, 360 angle. The function then returns the smaller angle as the result. The implementation is efficient, with constant time complexity O(1), as it involves only a few arithmetic operations. This solution handles edge cases, including when the hour is 12 or when the minute is 0, seamlessly by leveraging modular arithmetic and simple geometry. This is the Java implementation of LeetCode problem number 1344, angle between hands of a clock. The logic mirrors the Python solution provided, with adjustments for Java syntax and conventions. Key differences include explicit type declarations for variables and the use of Java's math library for absolute values and minimum calculations. This implementation calculates the angles for the hour and minute hands, finds their absolute difference, and returns the smaller of the two possible angles. The code is concise and adheres to Java formatting standards. Here, we start by calculating the angle of the hour hand. The formula to find this angle is hour %12 *30 plus minutes/60 *30. This formula accounts for both the hour's position on the clock and the additional offset caused by the minutes. Substituting the given values, we have 3 %12 *30 plus 15/60 *30. Simplifying, we calculate 3*30 for the hour portion, which gives us 90 degrees, and 0.25*30 for the minute offset, which adds 7.5 degrees. This results in a total of 97.5 degrees for the hour hand. Next, we calculate the angle of the minute hand using the formula minutes*6. Substituting 15 for the minutes, we get 15*6, which equals 90 degrees. So, the minute hand is at 90 degrees. Now that we have the angles of both the hour hand and the minute hand, the next step is to calculate the absolute difference between these two angles. The formula is abs, hour_angle, minute_angle, which gives us the magnitude of the difference regardless of which is larger. Substituting the values, we calculate abs, 97.5 to 90, resulting in 7.5 degrees. This represents one of the two possible angles between the hands. To determine the smaller angle, we use the formula min_angle, 360 angle. Substituting 7.5 for the angle, we calculate min, 7.5, 360 to 7.5, which simplifies to min, 7.5, 352.5. The smaller angle is clearly 7.5 degrees. Thus, the final output for this example is 7.5 degrees. For the next example, we have the hour set to 6 and the minutes set to 30. As before, we start by calculating the angle of the hour hand. Using the formula, hour%12, *30 plus, minutes/60, *30, we substitute the values to get 6%12, *30 plus, 30/60, *30. Simplifying, 6*30 gives us 180 degrees for the hour's base position, and 0.5*30 adds 15 degrees for the additional offset caused by the minutes. Adding these together, the hour hand's angle is 195 degrees. For the minute hand, we use the formula minutes*6. Substituting 30 for the minutes, we calculate 30*6, which gives us 180 degrees. So, the minute hand is at 180 degrees. With the hour hand at 195 degrees and the minute hand at 180 degrees, we calculate the absolute difference between these angles using the formula abs, hour_angle, minute_angle. Substituting the values, we compute abs, 195 to 180, which equals 15 degrees. This is one of the two possible angles between the hands. To find the smaller angle, we use the formula min_angle, 360 angle. Substituting 15 for the angle, we calculate min, 15, 360 to 15, which simplifies to min, 15, 345. The smaller angle is 15 degrees. Therefore, the final output for this example is 15 degrees. In this example, we set the hour to 12 and the minutes to 0. Starting with the hour hand, we use the formula, hour%12, *30 plus, minutes/60, *30. Substituting the values, we have 12%12, *30 plus, 0/60, *30. Since 12%12 is 0 and 0/60 is also 0, the entire expression simplifies to 0. Thus, the hour hand is at 0 degrees. For the minute hand, the formula is minutes*6. Substituting 0 for the minutes, we calculate 0*6, which also equals 0. So, the minute hand is at 0 degrees as well. With both the hour hand and the minute hand at 0 degrees, we calculate the absolute difference between these angles using the formula abs, hour_angle, minute_angle. Substituting the values, we compute abs, 0 to 0, which equals 0. This is the only angle between the two hands. To confirm, we determine the smaller angle using the formula min_angle, 360 angle. Substituting 0 for the angle, we calculate min, 0, 360 to 0, which simplifies to min, 0, 360. The smaller angle is clearly 0. Therefore, the final output for this example is 0 degrees. To determine the angle between the hour and minute hands, the solution breaks the problem into distinct steps. First, for the hour hand, we calculate its base position using the formula, hour%12, *30, which accounts for the fact that there are 30 degrees per hour. The modulo operation ensures the hour is within a 12-hour range, and both the modulo and multiplication are constant time operations. Additionally, the term minutes/60 *30 adjusts the hour hand's position to account for the fraction of the hour that is passed, using division and multiplication, both of which are O1 operations. So, the entire hour hand calculation is O1. Next, the minute hand's position is determined using the formula minutes*6, since each minute corresponds to 6 degrees. This involves a simple multiplication, which is also O1. Finally, we compute the absolute difference between the two angles using abs, hour_angle, minute_angle. This requires a subtraction and absolute value operation, both of which are constant time. Therefore, all steps so far contribute to an overall time complexity of O1. Now, let's consider the step where we determine the smaller of the two possible angles between the hands. The expression min_angle 360 angle ensures we always return the smaller angle, whether it's clockwise or counterclockwise. This involves a single comparison, which is an O1 operation. Since every operation in our solution, calculating the hour and minute angles, finding their difference, and determining the smaller angle is constant time, the overall time complexity remains O1. For space complexity, the solution is equally efficient. We only use a few variables, the input variables hour and minutes, which require O1 space each, and intermediate variables like hour_angle, minute_angle, and angle, all of which are floating point numbers that also require O1 space. Importantly, no additional data structures, such as arrays or lists, are used, meaning the solution's space complexity is also O1. When comparing this optimized approach to a brute force or naive method, the efficiency becomes even more apparent. A naive solution might involve simulating the clock hand's movement step by step. For example, iterating through each minute to update the positions of the hands or simulating an entire hour-long cycle. This would require a loop iterating 60 times for minutes or 12 times for hours, leading to a time complexity of O(n), where n represents the number of steps in the simulation. In contrast, the optimized approach skips all iterations by directly computing the angles using mathematical formulas. This eliminates the need for loops and reduces the time complexity to O1. The optimized method, therefore, is ideal as it leverages the inherent mathematical structure of a clock to achieve constant time and space complexity. Finally, let's justify why the solution has a big O notation of O1 for both time and space complexities. All operations used, modulo, multiplication, division, subtraction, absolute value, and comparison, are constant time operations, meaning their execution time does not depend on the input size. Additionally, the memory usage remains constant since the solution only uses a fixed number of variables, regardless of the input. There are no data structures or additional memory allocations that scale with the input. As a result, both the time complexity and space complexity are O1, making this solution not only optimal but also highly efficient for solving the problem of finding the angle between the hands of a clock. When solving this problem, there are some common mistakes to watch out for. First, remember that the hour hand doesn't stay fixed at the hour mark, it moves slightly as the minutes progress. For example, at 3:15, the hour hand is not exactly on the 3, it's at 3.25, which accounts for 15 minutes divided by 60. Ignoring this will lead to incorrect calculations. Next, always consider edge cases like 12 o'clock, where both hands overlap, or 6 o'clock, where the hands are directly opposite each other, creating a 180-degree angle. Testing these scenarios ensures your solution handles all possibilities. Another frequent error involves mixing up the clockwise and counterclockwise angles. To consistently return the smaller angle, use the formula min_angle 360 angle. Additionally, the minute hand moves 6 degrees per minute, but it's easy to make scaling errors in this calculation, so double-check your math. Finally, be mindful of floating point precision errors, especially in programming languages like Python or Java. Using integer arithmetic wherever possible can help avoid these small but significant mistakes. This problem is designed to assess your understanding of modular arithmetic and your ability to translate real-world scenarios into precise mathematical logic. A key insight is recognizing the relationship between the clock's structure and the angles formed by its hands. Since the calculations involve no loops, they operate in constant time, or O1, which is an important optimization highlight you can bring up during an interview. If you find yourself stuck, walk through specific examples like 3 o'clock, where the hands form a 90-degree angle, or 9:15, where the hour hand is slightly past 9. This demonstrates a structured thought process, even if you're still working toward the solution. Additionally, be ready to address follow-up questions, such as modifying the solution to return the larger angle instead of the smaller one, or adapting it to a 24-hour clock format. These kinds of variations are common in interviews and can showcase your flexibility and depth of understanding. There are several related problems that you may encounter, which build on similar concepts. For instance, the core problem, LeetCode 1344, focuses on calculating angles between clock hands. However, problems like LeetCode 31, next permutation, test your understanding of modular arithmetic and array manipulation, while LeetCode 12, integer to Roman, challenges your scaling and conversion logic. Another example is LeetCode 29, divide two integers, which emphasizes precision handling and arithmetic logic. In terms of alternative approaches, you could explore a vector-based geometry method. By representing the clock hands as vectors, you can calculate the angle between them using the dot product formula, which introduces trigonometry. While this isn't necessary for solving the problem, it may be worth mentioning if the topic comes up. Another approach involves simulating the movement of the clock hands incrementally. While this is less efficient, with a time complexity of O(n), it can serve as a teaching tool or a way to verify your solution. When comparing different approaches, there are some trade-offs to consider. The brute force method, which simulates the movement of the clock hands, is conceptually straightforward and easy to understand, but it's inefficient due to its O(n) time complexity. On the other hand, the mathematical formula is highly efficient, operating in constant time, or O(1). However, it demands careful attention to edge cases and precision to avoid errors. Another trade-off involves precision versus simplicity. Using integer calculations can eliminate precision errors commonly associated with floating-point arithmetic, but it may require additional scaling logic to handle the math correctly. Floating-point calculations are simpler to implement but can introduce minor inaccuracies, especially when working with very small or very large numbers. Understanding these trade-offs will help you choose the best approach based on the problem constraints and requirements. Great job! We've successfully solved the problem angle between hands of a clock. Remember, this type of question tests both your mathematical reasoning and your ability to write efficient code. Don't forget to practice similar problems, and we'll see you next time for another exciting challenge. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!